Question 20 on the 5 to 7 test. Sophie says, if n represents a prime number, then 2n plus 1 will also represent a prime number. Use an example to explain why she is wrong. So what this means is, if we put a number in for n, any whole number, then we times it by 2 and add 1, and this is saying we should get a prime number. So you might try 1, and it actually does work. For example, let n equal 5. That means we're going to get 2 times 5 plus 1, which is 11, and that is prime. So there's an example where it does work, but just because it works for this one doesn't mean it's going to work for everything. What about if we had n equals 10? Then we'd do 2 lots of 10, which is 20, add 1, which is 21. And 21 is not prime. For example, 21 divided by 3 is 7, so 7 and 3 are factors there. So we don't really need this top example, this was just one that we could rub out. So here's an example that shows that what Sophie says is wrong. It's not the only one, you could find other ones. For example, if you chose n equals 12, that's another example. There's lots and lots that you could use. Question 21 on the 5 to 7 test. A game has 6 rounds. In each round of the game, the player gains points which are added to their total score. The graph shows Sue's total score after each round of her game. How many points did Sue gain in round 4? Well, this graph here shows the total score after each round. Okay, it's the total score, it's not actually the score that happens in each round. But what we're going to do first is go across to 4 and draw a line upwards till it hits the graph, and then draw a line across. And we can see here, after round 4, she had 56 points. But she didn't gain 56 points in round 4, that's how many she had in total. So what we then need to do is think about round 3. And if we go up from round 3, and then across, we can see that after round 3, she had 45 points. So how many did she gain in round 4? Well, we need to do 56 take 45, and that gives us 11. So she scored 11 points in round 4. In part B, it says Derek plays the game. The graph of his total score after each round is a straight line. What can you say about the number of points Derek gained in each round? Well, if you imagine on this graph, he had a straight line anywhere, it doesn't matter where it is. Every round he's going up by the same amount of points. That would mean that in each round he is scoring the same amount of points. Question 22 on the 5 to 7 test. Inside the rectangle below is a shaded rhombus. The vertices of the rhombus are the midpoints of the sides of the rectangle. So what that's saying is that point there, there, there and there are halfway along the length and the width of the rectangle. Okay, remember, a rhombus is like a squashed square in the sense that all the sides are the same length. The question's asking us, what is the area of the rhombus? Well, one thing we could do here is draw a line straight across the middle and split this into 2 separate rectangles here. Because we know this is the midpoint, the length from here to here has got to be half of the total, so that's 4 centimetres. The top is 6 centimetres here, and this 4 centimetres is actually the height of each one of these triangles here. Now I'm just going to think about one of these triangles. The area of any triangle is given by half times base times height. And the base of this triangle is 6 and the height is 4. So we're going to do a half of 6 times 4. A half of 6 is 3, times that by 4, that gives me 12 centimetres squared. So the area of the rhombus is going to be 2 of these triangles, which is 24 centimetres squared. Question 23 on the 5 to 7 test. Part A says Sandra is thinking of 2 numbers. Her 2 numbers have a negative sum but a positive product. Give an example of what her 2 numbers could be. First of all, I'm going to think about how I can use 2 numbers to get a positive product. Remember, the word product means multiply. So my rules for multiplying numbers, if I have a positive and I times that by a positive number, you should know that I get a positive number. If I do positive times negative or negative times positive, I end up with a negative. And if I do negative times negative, that gives me a positive. So because I need a positive product, I either need this one or this one. So there's two possibilities so far, but they need a negative sum. And if I'm going to have a negative sum, that means I'm going to have to use this bottom one, because if I do a positive add a positive, there's no way I can get a negative number. So I want to choose two negative numbers, and it actually turns out that it won't matter which negative numbers we choose. So for example, I could do -3 and -3, because if I do -3 times -3, that gives me 9, which is positive. And if I do -3 plus -3, remember, if you've got a plus and a minus next to each other, that becomes a minus. This becomes -6, which is negative. So I'll choose those for my numbers, but I could actually choose any two negative numbers. In part B, it says Mark is also thinking of two numbers. His two numbers have a positive sum but a negative product. Give an example of what his numbers could be. Well, if he's going to have a negative product, that means that one of the numbers will have to be positive, the other will be negative. So we need one positive number and one negative number. And it says his two numbers need to have a positive sum. Well, let's say for example I chose -6 as my negative number and 3 as my positive number. Well, -6 plus 3 gives me -3, which doesn't work for this bit here. So that's bad. What I need to do is make sure that my positive number is bigger than my negative number. So it doesn't really matter what I choose. I mean, for example, I could choose -5 and 8. Because if I do -5 times 8, that gives me -40. And -5 add 8 is going to give me +3. So as long as my positive number is larger in size than the negative number, it won't matter which two numbers I choose. Question 24 on the 5 to 7 test. The mean of 5 numbers is 10. I add one more number and the mean is now 11. What number did I add? Let's first think about when we've got 5 numbers. If I've got 5 numbers, to work out the mean, I would add them up, which I'll call the sum, and then I would divide them by 5 because there's 5 numbers. Now, because I know the mean is 10, I can say that 10 equals the sum divided by 5. So using inverse operations here, that tells me that the sum will be 10 times 5, which is 50. Now let's think about if we have 6 numbers. Okay, the mean this time will be the sum divided by 6 because there are 6 numbers. And we know the new mean is 11, so we can say that 11 is the sum divided by 6. That makes the sum 6 lots of 11, which is 66. So when we had 5 numbers, they added up to 50, and when we had 6 numbers, they added up to 66. So that must mean that the 6th number must be 66 minus 50, which is 16. Question 25 on the 5 to 7 test. Solve these simultaneous equations using an algebraic method. So we've got 3x plus 6y equals 30 and x plus 6y equals 20, and it says you must show you working. First thing I'm going to do is label these equations 1 and 2. Straight away I can notice that both equations have a 6y in them here. So what I can do is make part of these equations cancel out, and I'm going to do that by doing number 1 subtract number 2. To help me do this, I've lined them up a little bit like a column sum. 3x take away x, which gives me 2x, 6y take 6y is nothing, and 30 take 20 is 10. So I get 2x equals 10, which means x must be 5. Next, I'm going to sub x equals 5 into one of these two equations here. I'm going to choose 2 because this will be easier to work with. So we've got x here, we're going to replace that by 5, plus 6y equals 20. Subtracting 5 from both sides gives us 6y equals 15. And then I'm going to divide through by 6. So that gives me y equals 15 over 6. I can cancel that down by dividing by 3, and I get 5 over 2. Notice I could also write 5 over 2, that's 5 halves, that's the same as 2.5 or 2.5. Either of those is fine for y. You can leave it as a fraction or a decimal. Question 26 on the 5 to 7 test. This shape is made of 4 congruent rectangles. Each rectangle has side lengths 2a and a. The perimeter of the shape is 80 centimetres. Work out the area of the shape. Let's start by adding some lengths onto a diagram. We've got an a there, 2a, and so on. And if we add these together, we'll start here. We get 1, 2, 4, 5, 6, 8, 9, 10, 12, 13, 14, 16. So we've got 16 lots of a, and we know if we add them all together, we should get 80. And if we divide 80 by 16, well, dividing by 16 is like dividing by 8 and then dividing by 2. Dividing by 8 gives us 10, and then dividing by 2 gives us 5. If you need to, you could always use a bus stop or write out your 16 times table for that one. Question 27 on the 5 to 7 test. The diagram shows 3 congruent circles drawn on an isometric grid. The area of this equilateral triangle here is y. The area of this segment here is w. It says write an expression using y and w for the area of a. Well, if the area of this triangle is y, and we've got w here, and w here, then that's going to give us y plus 3 lots of w. Question 28 on the 5 to 7 test. A pupil wrote, for all numbers j and k, j plus k in a bracket squared equals j squared plus k squared. Show that the pupil is wrong. All we need to do here is give a counter example. That's an example that shows it doesn't work for all numbers. It might work for some, but if we can show just one number that it doesn't work for, then we've shown that it's not true for all numbers. So let's, for example, try j equals 3 and k equals 4. So the left hand side will be 3 plus 4 in a bracket squared. Well, 3 plus 4 is 7, so that's 7 squared, which is 49. The right hand side though will be 3 squared plus 4 squared, which is the same as 9 plus 16, which gives me 25. And because 49 is not the same as 25, this isn't the same as this. So we've given an example with j equals 3 and k equals 4 where this isn't true. So if it's not true for 3 and 4, it's not true for all numbers.